Hey guys, welcome to my channel. My name is Adi. I'm a mechanical design engineer. In this channel, we'll be talking about a lot of things that's related to mechanical engineering. But today I would like to talk about one of my favorite topics, which is sheet metal design. We'll get started. So these are some of the critical design parameters when it comes to sheet metal. First thing is material. So material is the first and foremost thing. What material we are dealing with? Is it steel or aluminum or copper, brass, etc. Then sheet thickness, of course, and yeah, sheet thickness is basically a derivative of your design, and it could be decided based on what are your design considerations, other design consideration. Then we move on to K factor, which is also a criteria for bending, and then we're going to talk about bending direction, bend radius, cutting process, and forming methods. Here I have shown pictures of two broad categories of sheet metal parts, which is a bent part and a stamped part. So bending is basically a conventional press brake bending. So in case if you haven't seen a press brake, you can just go to Google and type press brake. You'll be able to see that machine. So which just makes one or maximum two bends at a time based on the you know tool that we use. Then stamped parts are basically tailored parts which are suitable for specific design requirements. It may be material stiffness or any formed features that serve a specific design purpose or for airflow and and to act as gussets, etc. So stamped parts actually require special tooling and it cannot be made with conventional bend. So stamped parts are usually costlier to develop compared to bent parts, although the piece part cost might be comparable or even cheaper than a bent part in some cases. So let's move on to discuss about each of these parameters. First, we talk about material. So I would like to focus primarily on steel and not go to aluminum or other materials. That could be a topic for a different day. But when we look at commonly available materials, we start with you know ASTM grades, which are like listed here, and then IS, which are Indian standards, and then GBs for China. So whenever you work for an OEM that's US based or India based, or basically I would say 70 to 80% of OEMs that deal with sheet metal parts, they would fall under these three categories. Of course, we have European standards and Japanese standard, but they would all be an equivalent of the ones that are listed here. There are other grades as well, but this overall category comes within ASTM or IS or GB for most of the sheet metal parts. And then when we talk about thickness, we categorize sheet metal into three categories. Basically, 0.2 mm or less, they are called metal foils, which are used for food packaging and thermal insulation, etc. And then 0.5 to 6 mm thick, that is where the technical sheet metal term comes into picture. But as a generic term, we can use sheet metal to represent anything. But when we want to be specific about it, between 0.5 to 6 is where sheet metal range lies. And then more than 6 mm, we call them plates. So more than 6 mm, it gets into structural high strength steel category. Now we can talk about K factor. So K factor is one of the design criterias or one of the manufacturing criterias more than a design criteria, I would say, which a design engineer should be aware of. So I would not talk about the extreme detail of a K factor here, but just enough for the awareness of a design engineer. K factor is basically a ratio between your neutral axis of your bent part and then the plate thickness. So neutral axis is actually a theoretical one. We do not know where the practical neutral axis of a part would be, but we have found that it ranges between 0.3 to 0.5, which basically means that you would find anywhere between one third of a distance or or half of the distance from your extreme fiber. So extreme fiber, I mean the innermost fiber during the bending process. So when you bend a sheet metal, there will be a line that does not experience any compression or tension. So that's what we call as a neutral line or neutral axis. So the location to that distance to that line from the extreme fiber to the thickness, that ratio is called the K factor. So the reason it plays an important role is in bend allowance calculation. So bend allowance is basically the amount of material that we have to provide for the sheet metal before bending so that the after bent length or the flange lengths are ideal as we expect from a design. Usually when we design something on a CAD model, we don't intuitively know what will be the unbent length or how much should be the flat pattern before we start bending it. So all this bend allowance and K factor comes into picture. So again, not going into the nitty gritty details, but these are all some broad terms that we should be aware of. Next up, we start with the bend direction and the grain direction for sheet metal. So they go hand in hand, these two terms. So the essence of bend direction here is usually how sheet metals are manufactured. We can think from a steel mill standpoint. Sheet metals are basically continuous castings that get rolled out of the steel mill. So when they're getting rolled, there is a particular direction in which the grains inside the metal structure are being formed. So based on the rolling direction and the way they're formed, so there is a particular lay of the internal grains and internal molecules inside the sheet metal plate. Okay, so the reason why we keep this as a key parameter in our design is because the strength of a material, although the material that we use as an isotropic material in terms of its absolute mechanical property, but there are other things that influence the mechanical forming process, the overall manufacturing process when it comes to grain direction. So here I've shown an image that indicates where the grain flow is. Maybe I'll turn on the pointer. So if we see here, so the material is bent in a way that the bend line is actually perpendicular to the flow of the material. In this case, the grains are actually oriented in the longitudinal direction to the bend angle. But whereas in the other case, as we see, this is the transverse bend line. So it is actually parallel to your bend, parallel to your grain direction or the grain lay. So here the material will be a little bit weaker compared to this, because a longer grain or the direction in which they are laid, it naturally contributes to a higher stiffness or higher, maybe I wouldn't say stiffness, but higher immunity to cracking. Because if the grains are laid in this direction, there is a high chance that the chemical bonds or the molecular bonds that are formed between the grain structure, they hold together very well in maybe in a fashion of a chain here. Based on the direction they are laid, the grains are longer, so that we are not hitting the discontinuous part of the grain anywhere in this bending direction. So they are all uniform, and we are bending it right in the middle so that they are continuous, and they are we are not breaking the discontinuous part of it. But if we are going to bend it in the transverse direction, we don't have much leeway when it comes to using a tighter bend radii or a shorter bend for a thicker part. So the reason being, as the grains are laid in this direction, we do not have much crossover between each grain on the bend line. So naturally what would happen is it will cause cracking. So that's why we usually choose to go with a higher bend radius, just to make sure that there is enough grains within our bending area to withstand the force that's coming from the press during the bending process. So the design considerations would be, usually try to align with the grain direction. I mean, the bend you should be choosing should, for the best interest, it should be a longitudinal bend. So we can go with a tighter bend radius, a smaller bend radius without cracking. But if you cannot do that in these types of scenarios, you can choose to go with the transverse bend line. But you need to choose equal bend radius just to make the manufacturing more easier, so that the operator who's doing this bend, he doesn't have to change the tool every time to make this part to perform these two bends. That would be my ask. And for complicated parts where the grain direction could not be directly aligned perpendicular or parallel to the grain to the bend lines, you can talk to your manufacturer to know what would be the ideal nesting part of the sheet metal. Because before the sheet metal is being bent, it will be put through a laser cutting machine, and you can get to know in what angle it's being placed before it's getting cut, so that you could be mindful. But yeah, so it depends on case to case basis. We can talk about more of that in later video. Moving on. Okay, now we can talk about bend radius. So bend radius is the most important parameter for a sheet metal design. The reason being, bend radius could be influenced by a lot of things. First thing is material. So the grade of metal that you are using, that decides how tight or how lenient could be your bend radius. And then the material thickness, and then The other thing is this bend direction also. So starting with the bend radius, we could categorize bend radius for softer materials and harder materials. Harder materials, I mean high strength materials that have yield strength more than 250 MPa. So usually for softer materials, you should target for a bend radius of at least 1 times plate thickness. So yeah, there is a typo here. It should be equal or less in some cases. It's not greater. And then for high strength materials, it should be greater than two times. And the thumb rule is if the material thickness is between say 2 to 6 millimeters, you can get away with 1 times thickness, irrespective of softer or harder material. But if the material is high strength and higher than 6 millimeter, you should definitely go for 2 times thickness. That's a thumb rule. Yep. Now coming to cutting and forming process. So this is something that's interesting and a broader topic. I'd like to shed some light on a briefer note here. So we can start with laser cutting. So one of the prominent ways of processing, pre-processing sheet metal before it's bent or punched or stamped. So laser cutting is the most widely used one, and we use plasma cutting for thicker parts as well, parts that are about 25-30 millimeter thick. But the mostly preferred one is laser cutting nowadays. A lot of manufacturers have laser cutting capability. And then coming to farming process, we can divide it into two, which is press brake bending, as I pointed out earlier. So press brake is the most conventional way of bending. So we have a V die, and then we have a press here. That's a tool, and then we keep our sheet metal, and there will be some stoppers to indicate the limit to which your flanges can extend out, so that we have a precise bending. And then coming to punching and stamping, these are extremely design dependent and are costly methods that involve a lot of tooling. And of course, there are some conventional stamping and punching process such as punching louvers, where there is not necessarily a material removal, but these are used for airflow, or sometimes they can also act as stiffeners on your design. In case if you're not having any external stiffening member or a gusset, this stampings could very well act as a maybe a stiffener and also a facilitator for airflow, which you might have seen in some places around you. So that's pretty much about basics of sheet metal design. Moving forward, I would be covering each of the topics that we saw in detail in the upcoming videos. So stay tuned for that, and if you have any questions or comments, please do let me know. Thank you very much for watching. See you guys in the next one.